Welcome to the sixth video in our vectors course. In this video we'll be learning about the dot or the scalar product. So hopefully at the end of this video you'll be able to define and calculate the dot product of two vectors and be able to find the angle between two vectors using the dot product. So let's begin by defining the dot product geometrically. If I wanted to find the dot product of two vectors, I have two vectors here, u and v. The method is similar for the parallelogram law of addition. I'd move the vectors together so that their tails are together. And if we let the angle between the two vectors be theta, the definition of the dot product, which is written as a dot, so u dot v, is equal to the magnitude of the vector u multiplied by the magnitude of the vector v and multiplied by the cos of the angle in between them. So that's the definition of the dot product, and while that might seem like an unusual way to define the dot product, we'll see why it's defined like that in a few minutes. Let's look at an example. Let's say we have two vectors here and we are asked to find the dot product. Let's say vector A has a magnitude of 5 units and vector B has a magnitude of 3 units. So A dot B is simply the magnitude of A, which is 5, multiplied by the magnitude of B, which is 3, multiplied by the cos of the angle in between them, which is cos of 30 degrees. And so our dot product is 15 root 3 all over 2. You'll notice that the result from the dot product is just a number, and that's another reason why it's called a scalar product, is because the result of the dot product is just a number or a scalar. We're going to look at the dot product or scalar product in component form. Here I have 3 points O, A and B and two vectors A and B, and we're going to call the angle between them theta. Because we're speaking in general, we'll set up vector A. We can say vector A is equal to A1i plus A2j plus A3k. Similarly, we'll name vector B B1i, B2j and B3k. We will need to use the magnitude of these vectors, so to work them out, we should know from before the magnitude of vector A all squared is A1 squared plus A2 squared plus A3 squared. Similarly, the magnitude of vector B all squared is B1 squared plus B2 squared plus B3 squared. We're also going to need the magnitude of vector AB. So vector AB is vector AO plus OB, which is minus A plus B. So the magnitude of vector AB all squared is the magnitude of B minus A all squared, which in terms of our vectors up here is simply B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared. We've got these now and we'll use these calculations in a minute. We're going to use the cosine rule on this triangle to find an expression for AB all squared. We could say vector AB all squared using the cosine rule is the magnitude of A squared plus the magnitude of vector B squared minus 2 times the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them, so cos theta. Notice that A times B, magnitude of B times cos theta is the dot product, so we can write magnitude of AB all squared, magnitude of A squared, magnitude of B squared, minus 2 times the dot product of A and B. We'll now rearrange this equation to make 2A dot B the subjects, so 2A dot B is equal to the magnitude of vector A squared plus the magnitude of the vector B squared minus the magnitude of AB, vector AB all squared, magnitude of B minus A squared. We'll now substitute in our values that we've worked out over here. So the magnitude of vector A squared we worked out just here. The magnitude of vector B we worked out here, and we have to subtract from that the magnitude of B minus A, which is this one here, which I will just rewrite in expanded form. Collecting like terms and expanding out here, we can see A1 squared take away A1 squared, and A2 squared take away A2 squared, A3 squared take away A3 squared, B1 squared take away B1 squared, B2 squared take away B2 squared, and B3 squared take away B3 squared, and left multiplying out the terms that are left, so we get positive 2A1 B1 plus 2A2 B2 plus 2a3 b3. And remembering that this was 2 times the dot product, and so dividing through by 2, we get the dot product of a and b is simply a1 b1 plus a2 b2 plus a3 b3. This is our definition for the dot product when the vectors are in component form. We'll have a look at a quick example to make this a little bit clearer. In effect, what this means is that to find the dot product in component form, all we need to do is multiply the components of each of I, j's and k's together. So an example here, the a dot b is you multiply a1 and b1, that is the components of the I components together, and add together the product of the j components, and add together the product of the k components. Let's look at an example of applying the dot product in component form. I have 2 vectors here, a and b. If you're asked to find the dot product, it's simply a matter of multiplying out components together. So a dot b is equal to 1 multiplied by 2, which is 2, and then negative 4 multiplied by 3, which is negative 12, and so the answer is negative 10. That's an example in 2 dimensions. Let's have a look at an example in 3 dimensions. Here we have 2 vectors in 3 dimensions. So a dot b, 2 multiplied by minus 1, which is minus 2, minus 1 multiplied by 3 is minus 3, and 3 multiplied by minus 1 is minus 3, and so we get negative 8. Putting the 2 versions of the dot product we know together, we can define the dot product as a dot b is equal to, in component form, a1 b1 plus a2 b2 plus a3 b3. But we also know that this is equal to the magnitude of the vector A multiplied by the magnitude of the vector B and multiplied by the cos of the angle in between them. This is useful because it's easy to work out the dot product given their component notation. So we can work that out, and given their component notation we can also work out the magnitude of the vectors. So what this means is if we can work out this part and this part, we are easily able to find the cos of theta, or the cos of the angle in between, or the angle in between them. Really, these 2 versions of the dot product allow us to work out the angle in between 2 vectors. We'll try an example to make that a little bit more clear. This example is from a VCE exam. You might like to take a few seconds to read it in your booklet first, and then we'll go through it together. So we're given 3 points in a plane, point A, point B, and point C. We're asked to find the cosine of the angle ABC. So we'll label that angle ABC as theta. So we have 2 vectors making up that angle, vectors BA and BC. So we want to apply the dot product to vectors BA and BC. So first we need to find out what vectors BA and BC are. Vector BA equal to A minus vector B, which is 2 minus 3i, which is minus I, and j minus minus j is positive 2j, and 0k minus k is minus k. Vector BC is C minus B, so we get 0i, take away 3i is minus 3i, minus 3j minus minus j is minus 2j, and k minus k is 0. We do need to find the magnitude of these vectors, so the magnitude of vector BA is equal to the square root of squaring the components, 1 plus 4 plus 1, which is square root of 6. And the magnitude of vector BC is the square root of squaring those components, 9 plus 4, which is the square root of 13. So applying the dot product now, we have vector BA dot vector BC is equal to, multiplying the I components together, we get 3, j components we get minus 4, and the k components we get 0. And we know that that's also equal to the magnitude of the 2 vectors multiplied together, which is square root of 6 times the square root of 13, and multiplied by the cos of the angle in between, which is cos theta. So rearranging this, we get cos theta is equal to minus 1 over square root of 6 times the square root of 13, and so the answer to the question is C. Of course, if you put this into a calculator, you can work out the angle theta to work out the angle between the vectors. There are some significant results from the dot product that we need to be aware of. First of all, if we reverse the order of B dot A or A dot B, it's not going to make any difference. So we can say that A dot B is equal to B dot A. The next important thing is if we have a dot product with the 0 vector, well, the magnitude of the 0 vector is going to be 0, so this always gives us a result of 0. Multiplying the dot product by a constant is the order will not matter. So we have the constant, which says k, and we take the dot product. The order in which we do it is not going to matter. So we could work out k times the vector a, and then work out the dot product with the vector b, or we could work out the vector b with the dot product of k and the vector b. The next thing to consider is if we take the dot product of a vector in itself, so a dot a, well, that's going to be equal to the magnitude of a times the magnitude of a, which is the magnitude of a squared, times the cos of the angle in between it, which would be, the angle in between of course is 0 degrees, and the cos of 0 degrees is just 1. So we get a dot product of a vector by itself is just the magnitude of the vector squared. Another important result to consider is if the dot product happens to be 0. So up here, if we've got our dot product, the only way we can get a 0 for the dot product is if either a or b or 0, the magnitude, so either one of these vectors is 0, or the cos of the angle in between is 0. If the cos of the angle in between is 0, it implies that theta is equal to pi on 2, or 90 degrees. And if we have a dot product equaling 0, this implies that the angle between the two vectors is a right angle. Either that, or either vector A or vector B are the 0 vector. This is an important result because oftentimes we're asked to find or show that two vectors are perpendicular. Another important result to consider is if you take the dot product and we get A multiplied by the magnitude of B. If the vectors are parallel, of course the angle between them will be 0, so we get cos of 0, and the cos of 0 of course is 1. So we just get the magnitude of A times the magnitude of B. If we get that result, we know that the vector is going to be parallel. We say the cos of the angle is 180 degrees. In other words, they're going in exactly the opposite directions. Cos of 180 degrees, or cos of pi, is minus 1. So we get minus the magnitude of A times B. This would imply that the vectors are parallel, they're going in opposite directions. And the final property of the dot product, which I won't prove here, but if I was in a classroom I would, is that the distributive loss. A dot B plus vector C is the same as A dot B plus A dot C. So that concludes our video on dot products. So hopefully you're now able to define and calculate dot product of two vectors and use that to find the angle between two vectors. In our next video we'll look at some problems involving the dot product to give you some practice at doing it.